On a quiet September morning in 2025, the James Webb Space Telescope, JWST, trained its gaze on a distant speck of light 40 light-years away, seeking clues about the potential for life beyond our solar system. In the vastness of space surrounding the small, dim star known as TRAPPIST-1, 7 rocky worlds silently orbit. Discovered in 2016 by the Transiting Planets and Planetesimals Small Telescope, TRAPPIST, in Chile, this ultra-cool red dwarf star, located about 40 light-years away in the constellation Aquarius, quickly became a focal point of astronomical interest. Among these worlds, TRAPPIST-1e stood out, residing snugly within the star's habitable zone, where temperatures could allow for liquid water, a critical ingredient for life as we know it. This zone, often referred to as the Goldilocks Zone, is neither too hot nor too cold, making it just right for an Earth-like environment. TRAPPIST-1e, in particular, captured the imagination of scientists and the public alike due to its Earth-like size and potential atmospheric conditions. Its orbit around its host star is tight. A year on TRAPPIST-1e lasts only about 6 Earth days. This close proximity allows for frequent transits across the face of TRAPPIST-1, offering researchers ample opportunities to probe whether the planet has an atmosphere by studying the starlight that filters through during each transit. The James Webb Space Telescope, JWST, launched in December 2021, was equipped with the advanced technology necessary to study these distant worlds. Its suite of instruments can capture extremely faint signals from the edges of the cosmos and is particularly suited to investigating whether exoplanets possess atmospheres at all. As TRAPPIST-1e transited its star, JWST's near-infrared spectrograph, NIR-SPEC, specifically its prism mode, recorded the starlight during multiple transits to search for subtle signatures that would indicate the presence and possible nature of any atmosphere. On that pivotal September morning in 2025, as TRAPPIST-1e passed in front of its minuscule star, JWST locked onto its target. The data streaming back to Earth was not just a series of abstract signals, it was a possible glimpse into a new world's secrets. This moment was the culmination of years of planning and hope, a testament to human ingenuity and the relentless pursuit of knowledge. As researchers explained, the goal was to determine whether TRAPPIST-1e retains any atmosphere, and if so, what kinds of atmospheres remain plausible, rather than to claim definitive detections of specific molecules. With each transit, the layers of data provided by JWST added depth to our understanding of TRAPPIST-1e. Early analyses in 2025 did not reveal a clear atmospheric detection. Instead, they ruled out some possibilities, such as a thick, hydrogen-rich atmosphere, and indicated that a Venus or Mars-like CO2-dominated atmosphere is unlikely. At the same time, a thin secondary atmosphere, for example, dominated by heavier gases, remains possible, as does the scenario that TRAPPIST-1e has little to no atmosphere at all. These results mark important constraints, but no confirmed detections of water vapor, methane, or carbon dioxide to date. As JWST continues observations, the scientific community watches closely for each new piece of data, each potential revelation about TRAPPIST-1e's atmosphere. The implications of these findings reach far beyond the confines of the astronomical community, touching on profound philosophical and existential questions about our place in the universe. The exploration of TRAPPIST-1e by JWST represents not just a technical milestone, but also a pivotal chapter in the human story, driven by our innate need to explore and understand the cosmos. As TRAPPIST-1e made its timely transit, JWST was ready, its instruments tuned to catch every photon that might carry a planetary signal. The James Webb Space Telescope, utilizing its advanced suite of scientific instruments, embarked on a critical observation campaign. One of these instruments, the near-infrared spectrograph, NIR-SPEC, played a pivotal role. As TRAPPIST-1 transited its host star, light from the star could pass through any atmosphere the planet might have, absorbing specific wavelengths depending on the chemical composition. This phenomenon, known as transit spectroscopy, provides a unique spectral fingerprint, which, with sufficient data, can be decoded to reveal an exoplanet's atmospheric properties, if an atmosphere is present. JWST's sensors captured this light, and scientists back on Earth processed the data with meticulous precision. What emerged in 2025 was a detailed but challenging spectrum, affected by the active, flaring nature of the TRAPPIST-1 star. Teams used these observations to constrain atmospheric scenarios for TRAPPIST-1e, rather than to announce detections of specific molecules. Each of these constraints carries profound implications. Ruling out a thick hydrogen envelope narrows the field of possibilities for habitability, while placing limits on CO2 helps refine models of surface conditions. The detection process is not merely pointing and observing. It involves complex calibration of JWST's instruments to differentiate between the light from the star and any light altered by passing through a potential planetary atmosphere. This calibration must account for variables such as the star's brightness, the planet's size, stellar activity, like star spots and flares, and the distance of the system from Earth. Researchers have emphasized that disentangling stellar effects from planetary signals is like listening to a symphony and separating each instrument, especially challenging around an active red dwarf like TRAPPIST-1. The question of an atmosphere on TRAPPIST-1e remains open, and that uncertainty itself is scientifically rich. A confirmed secondary atmosphere would suggest a dynamic planet, one that could potentially maintain conditions favorable for habitability. However, ideas about volcanism replenishing gases or the presence of a protective magnetic field are hypotheses at this stage and not confirmed by current observations. As such, they remain exciting possibilities to be tested by future data rather than established facts today. Each new James Webb Space Telescope study opens fresh vistas in the quest for extraterrestrial environments. The careful, step-by-step constraints on TRAPPIST-1e's possible atmospheres underscore an era where the discovery of life beyond Earth is not merely a possibility, but a steadily improving scientific search. As these results accumulate, they beckon us to rethink not only what we know about planets beyond our solar system, but also the very criteria we use to deem a planet habitable. This ongoing mission exemplifies the pinnacle of human curiosity and technological achievement, probing ever deeper into the cosmic unknowns, with every study refining our strategies in the cosmic quest for companionship in the vast universe. Against the challenges posed by an active red dwarf star, TRAPPIST-1e remains one of the most compelling nearby worlds to watch. Nestled in the constellation Aquarius, about 40 light-years away from Earth, it continues to be a prime target for JWST, as scientists work to determine whether it holds on to any atmosphere at all. While the current evidence does not claim detections of water clouds or specific gases, it does narrow the field, bringing us closer to answers about habitability around small, cool stars. This careful, cumulative approach doesn't just reshape our understanding of planetary atmospheres, it rekindles our age-old quest. Are we alone in the universe? Each piece of JWST data nudges us closer to answering this tantalizing question. As future observations build on today's constraints, the scientific community continues to test hypotheses and sharpen techniques. Understanding TRAPPIST-1e's atmosphere is like decoding a cosmic message across the expanse of space. Each clue tells us more not just about this planet, but about the potential for other worlds to host life. As we stand on the brink of potentially discovering extraterrestrial life or habitable environments, the role of technological advancements and international collaboration becomes ever more apparent. The Webb Telescope, a joint venture involving NASA, ESA, and CSA, demonstrates the power of global cooperation in unraveling the mysteries of our universe. With this steadily improving knowledge, our view of the cosmos and our place within it continues to evolve. As we keep watching and studying, each observation feeds into the grand narrative of our quest to find not just planets, but other places, other beings, other stories. As the light from TRAPPIST-1e journeys across the cosmos to Webb's mirrors, it brings not just data, but a humbling re-examination of our expectations. We now look to the skies not to claim early victories, but to gather careful evidence, step by step, about how many worlds might be out there, sharing this vast cosmic ocean with us. If you enjoyed this story, hit subscribe for more fascinating space and science deep dives every week. Thanks for watching.